Morning, ma'am. I'm M. Hemant Kumar from EEE Department from A section, and this is my presentation about electrical circuit analysis. The topic is Thevenin's theorem, Norton's theorem, superposition theorem, and reciprocity theorem. Introduction to Thevenin's theorem, Norton's theorem, superposition theorem, and reciprocity theorems. Thevenin's theorems, Norton's theorem, superposition theorem, and a reciprocity theorem are fundamental principles in electrical circuit analysis. These theorems help simplify complex circuits, making it easier to analyze and solve circuit problems. Understanding these theorems is essential for electrical engineers and technicians. We can see the example in this image. Thevenin's theorem states that any linear circuit containing several voltages, resistances can be replaced by just a single voltage in series with a single resistor. Next, Thevenin's theorem overview. Thevenin's theorem states that any linear electrical network can be replaced by an equivalent circuit comprising a voltage source with in series with a resistor R. The equivalent circuit represents the original network's behavior between two terminals. The theorem simplifies circuit analysis by reducing complex circuits to simpler equivalents. And the next, Norton's theorem overview. Norton's theorem is similar to Thevenin's theorem but represents a network as a current source in parallel with a resistor Rn. The Norton equivalent circuit is useful for analyzing circuits from a different perspective. It allows for easy analysis of current flow and power calculations in complex networks. And the next one is superposition theorem overview. We can see here in the diagram the circuit is given, and the superposition theorem states that in a linear circuit with multiple sources, the total response is the sum of individual responses caused by each source acting alone. This theorem simplifies circuit analysis by breaking down complex circuits into simplified components. It is particularly useful for analyzing circuits with multiple input sources. And the next one is reciprocity theorem overview. The reciprocity theorem states that the ratio of voltage to current between 2 points in a linear network remains the same when the positions of the sources are interchanged. This theorem is helpful in analyzing network behavior and understanding the relationship between voltage and current in a circuit. It allows for efficient analysis of networks without solving complex equations. We can observe in the diagram. And the next one, practical applications of Thevenin's theorem. Thevenin's theorem is commonly used in electronic circuit designed to simplify calculations and analyze circuit behavior. It is essential in determining the maximum power transfer in a circuit. The theorem is widely applied in industries where circuit analysis is required. Practical applications of Norton's theorem. Norton's theorem is utilized in circuit analysis to determine the current flow and resistance in a network. It is valuable in analyzing power distribution systems and calculating current requirements. The theorem finds applications in various electrical engineering fields. And the next one is practical applications of superposition theorem. The superposition theorem is used in analyzing circuits with multiple sources and determining individual source contributions. It is beneficial in troubleshooting complex circuits and optimizing circuit performance. Engineers often use this theorem in circuit design and testing. And the next one is practical applications of reciprocity theorem. The reciprocity theorem aids in understanding the symmetry of electrical networks and their behavior. It is valuable in analyzing signal paths and determining impedance relationships. The theorem is applied in communication systems and network analysis. Advantages of using Thevenin's theorem. Thevenin's theorem simplifies complex circuits, making them easier to analyze and understand. It helps reduce the number of calculations required in circuit analysis. The theorem allows for quick determination of circuit parameters and behavior. Advantages of Norton's theorem. Norton's theorem provides an alternative representation of a network aiding in current flow analysis. It simplifies calculations related to current sources and power distribution. The theorem offers a different perspective on circuit behavior, enhancing understanding. Advantages of superposition theorem. The superposition theorem breaks down complex circuits into simpler components, facilitating analysis. It enables engineers to isolate and analyze individual source contributions. The theorem is particularly helpful in analyzing circuits with multiple input sources. Advantages of using reciprocity theorem. The reciprocity theorem highlights the relationship between the voltage and current in a network. It aids in understanding the behavior of linear circuits and impedance characteristics. The theorem simplifies analysis by leveraging the interchangeability of sources. Limitations of Thevenin's theorem, Norton's theorem, superposition, and reciprocity theorems. These theorems are applicable only to linear circuits and may not be suitable for non-linear circuits. They require circuit elements to be linear and time invariant for accurate analysis. The theorems may not account for certain circuit complexities such as non-ideal components. Maximum power transfer theorem and compensation theorem. Maximum power transfer theorem. The maximum power transfer theorem states that maximum power is transferred from a source to a load when the load impedance is equal to the complex conjugate of the source impedance. This theorem is essential in designing circuits to ensure efficient power transfer and maximum utilization of power sources. Applying this theorem helps in minimizing power losses and optimizing the performance of electrical systems. Compensation theorem. The compensation theorem states that a network can be replaced by an equivalent network consisting of a single voltage source and a single series impedance. This theorem simplifies complex networks into more manageable models, making it easier to analyze and design circuits. By using the compensation theorem, engineers can effectively analyze and predict the behavior of electrical networks under different conditions. Practical applications of maximum power transfer theorem. The maximum power transfer theorem is commonly used in audio systems to ensure that speakers receive maximum power from the amplifier. It is also applied in power transmission systems to optimize power transfer efficiency between power sources and loads. Designing antennas for maximum power transfer in wireless communication systems also relies on the principle of this theorem. Practical applications of compensation theorem. The compensation theorem is widely used in filter design to simplify complex filter networks and analyze their frequency response. It is applied in control systems to model and analyze feedback loops, making it easier to design stable and robust control systems. Designing passive networks such as impedance matching circuits and attenuators also benefits from the simplification provided by the compensation theorem. The next one is conclusion. In conclusion, both the maximum power transfer theorem and compensation theorem play vital roles in the analysis and design of electrical circuits. These theorems help engineers optimize power transfer efficiency, simplify complex networks, and predict circuit behavior accurately. By understanding and applying these theorems effectively, engineers can design more efficient and reliable electrical systems for various applications. Maximum power transfer theorem is the load when the load resistance equal to Thevenin resistance as seen from the load or suffix L is equal to or suffix th. TH. Thank you, ma'am, for giving this opportunity.